Hello and welcome everyone. Thanks for joining our EDEM section today. My name is Cesar Barreto and I will be your presenter. I provide technical support to new and existing EDEM users, and I focus on producing e-learning material that will introduce you to current and new EDEM tools and will help you to speed up with the software. As we all know, many industries and applications involve ball and granular materials that are interacting with machines. And the use of altered EDEM software can really help you when trying to understand and optimize ball material handling equipment. This is the agenda for today. I will start with a definition of DEM, as it may be a new term for many of you. Then, I will give you an introduction to the altered EDEM software and the basics of how it works. We will do a short demo to demonstrate the EDEM interface and also the different components. And finally, I will show you an example when EDEM is coupled with MotionSolve. So let's start. DEM is a way of simulating discrete matter, in our case particles, that represent granular material, or any particle that we want to simulate. So in EDEM, the particles are assumed to be rigid, but small overlaps are allowed to represent deformations during contact. And because of the existence of those overlaps, we can calculate normal and tangential forces between the particles. Here is a simple example of three particles colliding. At the beginning, the particles are assigned with initial linear and rotational velocities. There is no forces acting on those particles. But then they move closer to each other and finally they collide, as we can see there. When they collide, overlaps are created and then we can have normal and tangential forces acting on those particles. Then the algorithm calculates the resultant forces and moments acting on each particle. Finally, numerical integration is used to update the linear and rotational velocities, positions, and orientations. So it can be seen in the animation how both linear and rotational velocities change during the collision. So DEM works when particles are in contact, and by applying a contact model that describes the physics of how particles will behave when they are in contact with each other or equipment, then EDEM is capable of calculating forces acting on those particles. And after updating positions, then the software looks for new contact with other particles or geometries. We get the updates and finally the whole process starts again. So this slide summarizes the basic principle of particle behavior when using EDEM. Granular material can be very complex, and a lot of engineers try to make sense how that affects their equipment and processes. So EDEM can be used in a wide range of industries, anywhere where ball materials are present. This includes the heavy equipment industry, looking at virtual testing of dump trucks, bodies. Here we have a truck excavator, also harvesters, and many others. It is also used in the mining and metal industry to test and verify performance of conveyor belts, transfer points, crushers, grinding mills, and also in the agriculture industry as well, as we can see here. That is EDEM coupled with MotionSolve, and I will explain an example later on during the presentation. We can also evaluate and optimize the design and performance of cars on different terrains. And we can model the interaction between the body parts and the soil. We can also simulate mixing processes, for example powders, and analyze the mixing effectiveness by showing the concentration of each type of particles in the mixer. Another industry is process manufacturing, where EDEM can be used to optimize process involving bulk solids such as powder mixing, tablet coating, milling, drying, and many others. You can really simulate so many different types of materials, including flexible materials. Now that we looked at some examples, let's move on and I'll explain how EDEM software works. when we set up a simulation, we want to be that simulation as close as possible to reality. And to achieve that, you have to define material properties, like the one shown on the left image. You have to define density, shear modulus, Poisson ratio. Then you have to define particle shape and also the size distribution that will give you a representation of the real material. And you will need all those inputs to start your simulation. Once you have all the input data, the next step is the calibration stage. And this is a real physical test that will ensure that your simulation shows real material behavior and also give you confidence that the simulation is representative to a real case. And that is what you want to achieve, a case scenario that is very close to your real application. And finally, on the right, we have the contact models. That are the physics laws and equations that describe the behavior of those particles when they're interacting between each other, and also, as I mentioned, the particles with the equipment as well. Here we can see the main 4 base models, and they are used for different kinds of materials. They are all based on quantum mechanics theories. For instance, the JKR introduced attractive forces to the particle. We also have the Hertz-Milne, that is the default model in EDEM, the EDEM model that is used for stress-dependent material, and his theoretic spring model. I won't go into details about quantum models, as this is not the aim of this presentation. However, here we can see a schematic of the different EDEM quantum models. So you can choose one of the base models, then a rolling friction model and additional models. You can chain them together to best represent your application. And all these components combined together produce a fit-for-purpose ball material flow behavior, and that's what we want to achieve. Now let's move to the next section. For the EDEM demo, we're going to do the mixing tutorial. And in this demo, I'm going to present the 3 different components of EDEM, starting with the EDEM Creator, where we set up the model, then the EDEM Simulator, where we run the model, and finally the Analyst, that is the post-processing section of EDEM. Let's start with the EDEM Creator. Here we have the Creator interface, and the first thing we have to do is to set the measurement units. Once we do that, then we move to the Creator tree, and we work our way from top to bottom. First, define the granular material. Right-click and select Add Ball Material. Then you have to define the material properties. That includes the Poisson ratio, solid density, and the properties we spoke at the beginning of the presentation. Then you have to define material interactions, and that includes the coefficient of static friction, coefficient of rolling friction. All these material properties are very important, and you should get that information from literature or previous projects. However, if you don't have that information at all, I will show you after the end of this first part of the Creator which tool you have available in EDEM to help you to start with this. After that, it's a good practice to rename the ball material, and in this case will help us to identify the different particles that we're using in our simulation. Next, we have to create the particles. Remember that the particle shape in your simulation, it will depend on the kind of analysis you would like to do, and also the dimension of your particles. For this demo, we are going to create a 3-sphere particle. So we just add a particle and then create and position each of those spheres. The radius of each sphere is 3 millimeters, which is quite a large particle. Also on the left-hand side, you have the shape library that will help you to start with any of those default particle shapes. And also on the right, you have the particle generation tool that will allow you to import a CAD template, and then EDEM will generate those particles based on that template. Next, we have to set the particle size distribution, and this will provide you some real behavior to the material. However, Keep in mind that if you have a large size distribution with tiny particles and large particles, that will impact your simulation time. For this example, we are using a fixed size distribution. Also, anytime that you do any modification to your particle, remember to press Calculate Properties. Next, we're going to rename the particle and call it base. After this, we're going to duplicate the particle because we have three different types of particles: base, middle, and top. Right-click on your ball material and create 2 copies. After that, you have to rename the ball materials and the particles. And this is what you should get. Next, we have to define the equipment material. And in the same way, we just right-click on the equipment material and then we rename it steel. In a similar way, we're going to define the steel properties and also the interactions with the 3 different tablets. Once all the ball and equipment material are set, the next step is to move to the geometries section. And in here is where we import all the CAD geometries that we're going to use and also to add any motions and kinematics. Then right-click on geometries and import the CAD geometry. Once you select the CAD geometry, you have to specify the units. Click OK. And for our demo, we are going to merge all the blades parts in one. So right-click, press Merge Geometry and select them all. Now, we're going to rename it as blades. And also, we're going to rename the other geometry as a drum. In EDEM, you can define different kinds of kinematics. You can define translation, rotations, and also sinusoidal kinematics. We also have force and torque controllers, where you can input a time-dependent equation to specify the force or torque on your equipment. For our case, we have to set the initial velocity and also to set the axis of rotation. The display vector is very useful, so you will know if the axis of rotation that you have assigned is correct. After this, we are going to copy the rotation motions to the blades, as they have the same kinematics as the drum. Now we have to create a factory. And remember, a factory is the term we use in EDEM to introduce material or particles into the simulation space. So right-click on the geometry that you will use as a factory, in this case it's a drum, and a factory, and we're going to rename it. In EDEM, we have 2 different types of factories, static factories and dynamic factories. In this demo, we're going to use a static factory, and the difference is that static will create all the material in one time step. Then you have to set the particle generation properties and select the material. Remember, we are creating 3 different types of material that are the 3 different tablets. After this point, we're going to copy the factory base twice to create factory middle and factory top, and we're going to rename it. I won't show you the details of how to create the other 2 factories, as it's exactly the same what we did with factory base. And here we have the 3 factories created. Next is the physics sections. And this is the section where we define the contact models we want to use. For this example, we're going to use the Hertz-Midland contact model, that is the default model in EDEM, for both particle-to-particle and particle-to-geometry. And finally, we have the environment section, that is the final section of the creator tree. These are all the different parts of the creator tree. And now we can save the model. Okay, so now that we finished setting up our simulation in the EDEM Creator, I'm going to give you some guidance on how you can optimize your simulation. We're going to cover 3 sections: factories, creating materials, that will be your ball material, and then geometries. Let's start with factories. A factory is a term we use in EDEM to introduce material into the simulation space. So in this part of the presentation, I want to give you some tips how you can improve or optimize your factory. The key point here is that no particle will be created that touches another particle or a geometry. And because of this, it is important to make sure that your factory geometry have the correct size for the creation rate that you're using, the one that you set. Otherwise, you will find the EDEM struggles to find a space for particle creation, as you can see in this video. And if you think your simulation is running slowly because of factory settings, you can resolve this. Move to the EDEM Creator and then increase the size of your factory geometry. Also, you can lower the creation rate. And finally, you can assign an initial velocity to the material. Another point that you should keep in mind is check your solve report. In here, you can see if you have a high number of particles regenerated. That's an indication that your simulation is running slowly because of the factory. So what we're going to do is adjust the factory settings and see what happened with the solve report. We're going to reduce the generation rate, save the simulation, and then run the simulation again. We clearly see that the material is flowing so much better. If we stop and then check the factory, now we can check the particle properties, and there is some regeneration. However, there are no particles that fail, and that's an indication that our factory is running as expected. Let's go into the second section, that is creating materials. And at this point, if you remember in the demo, we have all the properties of the material like density, Poisson ratio, and so on. If by any chance you don't have that information, then EDEM comes with a series of material model libraries that you can use as a starting point for the simulation. So first we have the GEM database that is based on the angle of repose and the inclined plane test. In here, you only need to answer 3 questions about your material to obtain a material model. The questions are, which is the size of your application? So you just select roughly which is the size, then what is the pole density of your material? And finally, what is the angle of repose? That is a test that you will do. Here you have a table where you need some engineering judgment to choose the correct material. All depends if you have a free-flowing material or a sticky material. Once you select your material, then you will be presented with a table. And in this table, we can see the final material properties and also coefficients that you will use in your simulation as a starting point. Once you click Finish, you can see that the ball and equipment materials have been assigned in your EDEM Creator. Also the particles as well. And the final material model library is the powder starter pack. So powders are used in different applications in the pharmaceutical industry, also additive manufacturing, and chemicals and other process manufacturing industries as well. This powder starter pack is designed to be useful for anyone that would like to start your simulation, obviously using powders. And it has a selection of 9 material models, and they represent a range of materials with different flow properties and also compressibilities. And all these models use the Edinburgh elastoplastic addition model. Have been designed to simulate these complex cohesive materials. And we can see the table on the right. In this video, you can visualize the difference in mixing free-flowing powder and cohesive pure-flowing powder. In the same way, you have different folders with all the 9 material models to choose from. And finally, to finish with the creator component, we have the geometries section. In here we have the parent-child feature. So this is used to link the motion of geometries together, so that complex simulations can be defined in a fast and a simple way. And you just have to define which is the parent and which is the child. And we can see here, so the first object, we define the kinematic, and then that kinematic is kept, and we just transfer that to the second and third object. And we can see in this example of a mixer. Also, you are able to replace geometries, and this is useful in the case you want to investigate different designs. And finally, I would like to point out that you have this multiple copy option where you have to define only once the kinematics, and then that kinematic can be transferred or can be copied to the other ones, and with a delay time. And we'll see here how it works. So we can see at the moment, only for one object, the kinematic has been defined. But then we can create multiple copies. And those kinematics that we define for object number 1 can be copied to any number that we can define here. We just need to tell the software what is the delay time. So when we save the simulation and then play, we can see what's happening. We can create the object 1, 2, 3, all following the same kinematics as the first object that we set. And that's it. That's what I wanted to mention regarding the creator. So let's go back to the EDEM demo. And the next component is the EDEM Simulator. This is the interface for the simulator. And here is where we run the simulation. On the left-hand side, we have to set different parameters, and that includes the time step, that it should be small enough to guarantee stability in the simulation. And that will depend also on the contact model and material parameters. We also set the total simulation time and the simulator grid. You will have the option between CPU and GPU engine, and you can also choose between OpenCL or CUDA solver. And once you have all this set, then you can press play. So as we all know, EDEM is a very computational intensive method, and speed is always a key aspect for simulations. So in the next section, I'm going to give you some guidance on how you can speed up your simulation and some of the parameters that you can check to see if you can change it and then run a simulation quicker. Once we reach the total simulation time, we are ready to analyze the results and move to the EDEM Analyst. But before that, let's see some guidance regarding the EDEM Simulator. I'm going to mention the key parameters that you can modify to speed up your simulation. And the first parameter that I'm going to mention is the shear modulus. So this shear modulus value has a significant effect on simulation time step. And remember, the time step is very small in EDEM. Otherwise, we could experience a strange particle behavior, like exploding, for example. And typically, the shear modulus value can be decreased to speed up the simulation without any effect on your results. And this is something that we usually mention because users want to use the real shear modulus of the material, when in reality, they can speed up the simulation by decreasing this value. The second parameter that has a significant influence on the computational time is the number of particles. that we use to represent a particle shape. And that makes sense because then we will have more context, so more calculations. So the rule here is simple particle shapes are often enough to capture the ball behavior. However, when you have those cases where the particle morphology is well defined, for example, tablets, then you can use the particle generation tool in EDEM to help you to create those shapes. Also, particle size distribution is another way of keeping realistic material behavior. But sometimes, when we have finds in the simulation, we could remove those small particles. Often finds don't have a significant effect on the ball material response, and the reason is because the mass fraction of the fine particle is very low, especially if we are talking about coarse materials. And if you can remove the finds, then you can reduce computational time. Also, you can upscale the particle mean size and maintain the particle size distribution in your model. And by doing this, you can still capture the particle size segregation effect. In here, you can turn compressed data on or off. So if it's off, it will save some CPU power. However, your file will be larger. Also, you can reduce the save data frequency. And as well, you can select which data you would like to save. That will also speed up your simulation. And finally, for large simulations with thousands or millions of particles, we also recommend using a GPU engine. And that's pretty much all the guidance for this part of the presentation. I will explain the last component of the software, that is the EDEM Analyst. We're going to go back to the EDEM demo. And before I start, remember we started with the creator, where we set up the model. Then we switch to the simulator, where we run the simulation. And now the EDEM Analyst, that is the post-processing section of EDEM. First, we're going to assign different colors to each of the particles. Started with the base particle. And in the same way, we can color the middle and the top particle. After doing this, we are gonna play the simulation and see what is happening in the mixer. And we can actually see what's happening after 2 rotations in the mixer. Next, I will use selections. Selections allow to monitor particles passing through a volume known as a bin. For example, you can use them to determine the mass flow analysis within a specific region. In our example, we're using bin groups to determine how many particles are in that specific area. Here there is different options where we can set the bins. Including the dimensions and also the display option. We can all have the options if we want to always see it or only when it's populated. Next, we will create 3 queries, one for each particle type. And that will allow us to determine how many particles are in each bin. Then I do some subsection coloring to see the particles distribution throughout the simulation. The different colors give an indication where the particles are accumulating. And this is done for each time step. And also you're able to display the numbers of particles in each bin. To do that, you have to turn on the auction. And here we can see the exact number of particles we have selected. And in this image, give you a representation of the kind of analysis that you can do and to understand the mixing efficiency of the equipment. We can also create plots within EDEM to analyze our results. And in here, we're going to determine the contact forces between layers. You have to select the right attributes and also the settings to generate your plot. Once the graph is created, it will give you a better insight of how the equipment is working and also on how the base and top particles are getting mixed. As we can see in the plot, there are no contacts at the beginning of the simulation. However, as time passes and the drum spins, there are more and more contacts between the base and top particles. In the same way, you can do it for the other type of particles. And we can see the number of contacts between the base and middle tablets. Also, if you would like to plot in any other post-processing tool, you're able to export this data. In this final part of the EDEM Analyst, I would like to highlight some more examples when using selections. Also, talk about sensors. And finally, I would like to highlight some of the tools that are available to create dynamic videos in EDEM. So let's start with the examples. Here we have a mixer, and all those three bands that you see there, those three different colors, they were created using selections. And they are used to analyze the mixing efficiency of the equipment, in this case, a mixer. In here, geometric beams were set up to track the material passing through the sections of interest, and we have created two boxes, one blue color one or purple one, and kind of a pink one. And finally, we have this graph bucket, where we can use selections to understand the handling of different materials. And as well, we can track the amount of material moved with different operational settings for the graph bucket from one box to the other one. We can also investigate which is the ideal speed of the bucket to avoid spillage. Also, you have sensors in the EDEM Analyst, and they will allow you to measure mass flow rate, total mass, density, and velocity of your ball material. When you use sensors, you are able to see the numerical value on the screen, but also you are able to export that data or do the plots in EDEM. And the way we do the setup is very similar to selections. So you just right-click and select any of the sensors available. Then we have to do the settings. So what I mean is you have to select if you want to see the sensor always or only when it's populated, also the geometry, and then the location and the dimensions of that sensor. One other thing, the sensor's position can be linked to a geometry, and this is useful when analyzing moving material with geometries. So this bucket elevator tutorial shows different sensors, which help to analyze the process via visualization. Or you can use some plotting as well. For this tutorial, we will plot mass flow rate for sensor 1. And here, and we can see. And finally, we can see a vibration screening process, where total mass sensors were added to measure the total pass mass at each different deck. So we can see number 1, 2, and 3. And finally, let's check the last point, that is how you can create videos in EDEM. EDEM has the ability to track a geometry, and this is very helpful when your simulation includes many moving parts and you are interested in one specific object. For example, here, the green bucket. First, you must create a new camera view and save that view to a system view, as you can see at the top there. Then edit the view and tick the Track Geometry box. Set the camera view and positions, and once you're ready, click Apply. And finally, we have the Playback Scheduler. In here, you can change the view when creating your video. And this is useful if you want to compare different designs. So you have to create and name each of the views that you would like to have. After that, you are able to import or export any view already created. And this tool is useful for comparison when you are running different simulations and want to compare different designs or different material floors. Then you have to tell EDEM when you want to apply the view that you already saved. And in this example, we can see how first we want diameter, then it changed into velocity, and finally we change the view. And this takes me to the end of the EDEM demo, where we cover the three components: the EDEM Creator, the EDEM Simulator, and the EDEM Analyst. Now, let's move to the last part of this presentation, that is the EDEM and MotionSolve example. EDEM can be coupled with other altered tools, including ArcuSolve, SimSolid, and MotionSolve. Today, we're going to see an example between EDEM and MotionSolve. The EDEM MotionSolve coupling transfers the ball material load directly from EDEM into MotionSolve. Then the ball material loads are used in MotionSolve to understand the effect on the equipment dynamics. The objective dynamics are passed back to EDEM to provide a realistic force feedback throughout the simulation. Here we have an excavator model that is already set up in MotionSolve, all the geometry, graphics, forces, and motions. And the model is ready to be run. In the same way, we have already set up the model in EDEM. We have defined the ball material properties and also the physics that are the contact models. Also, we have created a factory. In this case, the factory is moving, and in this way, we are providing more space for the particle to be created. Then we move to the simulator and we run the simulation. Once all the ball material is created, we can save the simulation. We can go to the analyst and then export the simulation at the last time step. And then we set the time to 0. In this way, we are creating an EDEM simulation where the ball material has already been generated. Also, we can remove the factory geometry because we don't need it during the EDEM and MotionSolve coupling. Then we can adjust the domain. Once your simulation is all set, you can start the coupling server. In MotionSolve, you can create the EDEM subsystem, and here you have all the tools to couple with EDEM. The aim of this short video is to show you the type of analysis you can do when EDEM is coupled with MotionSolve. However, for any of you that is interested in the full details of how to couple EDEM with MotionSolve, there is a dedicated course in the Alter EDEM e-learning and is available in the website. Once the requested code simulation time is complete, then you can analyze the results in EDEM and also in Hyperview. You can estimate stress and loads from the ball material interaction with the excavator. In this example, we can see the stress on the equipment part when handling two different ball materials, called an iron ore. And this is the end of the presentation. But before we start with the Q&A section, I would like to point out that we have an EDEM e-learning section on the website where you can find much more details and further information about the tools and the EDEM components that we covered today. And thank you very much for your time today.